So as an overview, in part one, I'll be finding the mass of the black hole. In part two, I'll be attempting not to crash a spaceship when attempting to exit the atmosphere of the planet orbiting close to the black hole. And the discussion questions we will discuss later is what if for part one and what does it mean for part two. And for the coding, I'll be using the WebVPython software. So some key concepts are Newton's second law, which is F net equals dp over dt, and F net equals F net parallel plus F net perpendicular. And then the gravitational force is another key concept. The force of gravity equals the gravitational constant times mass 1 times mass 2 over r squared times r hat. And then we could use that formula to find mass 2, which we'll be needing to do for question 1, part 1, to find the mass of the black hole. So here's the code. So on the left side, we establish some initial properties, like the gravitational constant, the mass of the star, the change in time, and the velocities. So for the calculation loop, first we use the velocity components and define the initial and final velocities. And using these initial and final velocities, we can calculate the initial and final momentum by multiplying the mass of the star by the initial velocity, mass of the star by final velocity. We can also calculate the change in velocity and change in momentum by subtracting the initial velocity from the final velocity and initial momentum from the final momentum. We can calculate dp dt. That is equal to delta, the change in momentum, over the change in time. And then F net is dp dt. So we can calculate dp dt parallel and dp dt perpendicular, separating the components of this motion. And then we use all this to calculate the mass of the black hole. So the mass of the black hole is equal to the magnitude of the net force times the magnitude of the position of the star times the magnitude of the position of the star again. So the magnitude of the position of the star squared over gravity times the mass of the star. And we, on this, for the code continued, this left side just shows me establishing the arrows pointing inward, showing centripetal acceleration. So for the final results, F net equals 8.58 times 10 to the 28th, and F net parallel equals 2.43091 times 10 to the 28th. F net perpendicular equals 8.21746 times 10 to the 28th. And the mass of the black hole is 1.13 times 10 to the 34th. Here's a video of the motion. You can see that in the video, these numbers correspond with the video numbers I showed yesterday, or last slide. So for part two, don't crash, the key concepts are the same, which is Newton's second law, which is aka the momentum principle and the gravitational force. So here's the code. On the left side, we just established some constants, like the mass of the black hole equals 1.13 times 10 to the 34th, and some other constants that I discussed in part one. So on this left side and bottom left and bottom right side, we are establishing the net force on the planet and the net force on the ship. You calculate the net force on the planet by finding the force that the black hole exerts on the planet and the force that the ship exerts on the planet and adding those two together. And for F net on ship, you add the force that the planet exerts on the ship and the force of the black hole that exerts on the ship and add those together. And up on the top right, we're just establishing some initial conditions for the motion of the planet, like the speed and velocity. And so here we're able to, this code visualizes what was discussed on the previous slide by using the position and velocity update formulas for both the planet and the ship. And the code will break if the velocity is not great enough to exit the gravitational, the force of gravity for the planet and the black hole. And it'll say, oh, it crashed into the black hole or planet. So using some numbers I found due to trial and error, was the ship to exit the orbital radius of the black hole. That pink line is actually the ship. And you can see it kind of slingshots past the black hole, where the blue line is the planet. So some discussion questions. In your analysis, you for part one, You should discuss how the net force and its parallel and perpendicular components are different from the rate of change in momentum. So F net equals dp over dt, as I discussed in the key concept slide. In part 1 of the lab, we were measuring 4 dp dt, and therefore we were concluding that the net force was equal. We just deduced the value of F net. Instead of wanting to take a quick look at the black hole and leave, what speed would the ship have to go for it to travel in an orbital radius of the black hole? So using the numbers I